So welcome back, everyone. As usual, we have a couple of minutes before the official class start time. If you have any questions, feel free to ask them now. If you have any questions. Okay, so today's lecture is going to be about two kinds of random variables that you may have heard of before, but probably you've heard of them as being called distributions. And these are the so-called geometric and binomial random variables. Two sort of really important kinds of random variables that come up frequently. So it's good to recognize them when we see them, so that we know what we know the basic facts about them, in particular their expected value in this case. So to start with, just let me remind you of some things from previous classes. So we have seen these geometric series, which are sums of the form from I running 0 up to n of x to the I, where x is some value typically between 0 and 1. And we proved this, so we saw the finite version of this sum, where it runs only up to some capital N, and proved that it's equal to that. That was just an easy rearrangement. Then Then if you take the limit as n goes to infinity, you get this infinite sum. And that means you also take the limit on this side, and you get 1 over 1 minus x. And that's true as long as the absolute value of x is smaller than 1. And we didn't do this, but you can see that if you take the derivative of this sum with respect to x, and if you remember at all how to take derivatives, then the derivative of a sum is you just take each of its terms and take its derivative, and the derivative of x to the I is I times x to the I minus 1. So that's the derivative of the left-hand side. And if you remember how to take the derivative of these kinds of things, you'll see it's 1 over 1 minus x squared. So from this infinite sum, we get an identity by taking the derivative of each side. We've also seen this thing, the nth harmonic number. That'll show up today. It's just the sum 1 plus a half plus a third plus a quarter plus an eighth and so on, all the way up to 1 over n. We can't take this one to infinity because that sum is closely related to, it's bigger than ln n, and it's less than or equal to 1 plus ln n. So if we put infinity up here, then we get ln of infinity, so that the infinite sum doesn't exist. The limit is infinity. And what I'm about to show you is this one now that we'll use today. This is a really handy one to remember. So we've seen two definitions of expected values, two equivalent definitions, one in which you sum over all the possible outcomes, the probability of that outcome times the value of the random variable at that outcome. And the other is you sum over all of the possible values of the random variable, that value times the probability that the random variable takes on that value. And here we'll see that for certain kinds of random variables, there's another version of expected value which is sometimes simpler. Okay, so here's a lemma that captures the thing on the right. So if I say if x from, so remember a random variable is a map from a set of outcomes to real numbers, and in this case I'll restrict it to be integers and non-negative ones. So x maps from outcomes onto non-negative integers. So that's called a non-negative integer valued random variable. Then the expected value of x is actually equal to the sum I equals 1 to infinity of the probability that x is bigger than or equal to I. Okay. That's strange. That doesn't look anything like our other definitions of expected value. All those other definitions of expected value, they had in them some probability that x takes on a particular value or some value in a set, but that was always multiplied by something like the value of x, and that disappears here. And the proof of this is easy. So here's the proof. For each I in let's say 1, 2, 3. So all the positive integers, let pi equal the probability that x equals I. So x takes on all these different values. So for each value, there's a particular probability that x takes that value. This could be 0, for instance, if I mean, this is an infinite number of these i's, and maybe x only takes on a finite number of values. That's not a problem because these pi's can be 0. So we'll define that. And then notice that the probability that x is bigger than or equal to I. So when is x bigger than or equal to I? Well, x is bigger than or equal to I if it's equal to I, or it's equal to I plus 1, or it's equal to I plus 2, or it's equal to I plus 3, and so on. I mean, that just means that this is equal to the sum j equals I to infinity of the probability that x equals I, which is, if we write it out longhand, that's just pi plus pi plus 1 plus pi plus 2 plus pi plus 3, and so on. Nothing special there. Formally, here we are applying, from this step to this step, we're applying the sum rule. We have this set of outcomes where x is bigger than or equal to I, and we break it up into, we partition it into disjoint sets, which are when x equals I, x equals I plus 1, x equals I plus 2, x equals I plus 3, and so on. Okay. Good. Now we're almost done. Let's just write down this sum and see what pops out. The sum I equals 1 to infinity of the probability that x is bigger than or equal to I. Well, the first thing in there is the probability that x is bigger than or equal to 1. So that, the probability that x is bigger than or equal to 1, we can use this, and we see that it's just p1 plus p2 plus p3 plus p4 plus p5, and so on. Now the second term in this sum is the probability that x is bigger than or equal to 2, and we can use this again. So it's going to be this infinite thing, but instead of starting at 1, we start at 2. And so on. And the third sum is the third term is the probability that x is bigger than or equal to 3, which is just this. And we keep going like this forever. Now, let's see what we have. So we have, if we look at this column by column, well, we see that P1 only appears once here, right? It only appears in the first thing, the first row, which corresponds to the probability that x is bigger than or equal to 1. And so if we add all of this up, well, one of the things that we get in our total sum is 1 times P1. Now, P2 appears in the first one because it happens when you're equal to 2, you're bigger than or equal to 1. And when you're equal to 2, you're bigger than or equal to 2. So it appears twice. We get 2 times P2. And similarly, 3 times P3. And so on. So if we write that out as the infinite sum, we're getting the sum I equals 1 to infinity of I times pi. But that's just the sum I equals 1 to infinity. The definition of pi was that's just the probability that x equals I. But wait a minute, the sum I equals 1 to infinity of I times the probability that x equals I, that's just the expected value of x. Right. This was one of the two definitions we had for expected value of x. So this sum, the probability that x is bigger than or equal to I, is actually the same thing as the expected value of x. And that's just because each pi occurs exactly I times in that when you expand the sum. And the only thing to watch out for is, this has to be true for non-negative integer valued random variables. And if you've taken a stats course where you've learned about geometric, the geometric distribution and the binomial distributions, you may have learned also, well, hopefully you learned something about expected values, and you may have seen there that there were sort of two ways of doing expected values, and one of them looked like this, but there was an integral. So this is the same thing happening, but just in the discrete setting. And sometimes, depending on the stats course, you may not have proved it, but here's a proof, at least for the discrete setting. So that's what this says here. So we're keeping track of this thing over here. Okay. So ask me any questions about that if you like. Actually, I'll leave that up and put the definition here. So let's start with a geometric p random variable. So the best way to think of this is we have a biased coin that if we toss that coin, probability of heads is equal to p, and the probability of tails is equal to 1 minus p, and here p is something between 0 and 1. So for a usual coin, p is a half, but this is a biased coin. Maybe it's more likely to come up heads or tails. And we repeatedly toss the coin until the first heads. So if we do that experiment, so the coin tosses are independent. So I toss it, it comes up tails, I toss it, it comes up tails, I toss it, it comes up tails, until eventually I toss it, and the first time it comes up heads, that's what you get. Then the number x of coin tosses is what's called a geometric p random variable. And in a stats course, you would say that x has a geometric p distribution. So we've actually seen this before. And where have we seen it? Well, we actually did this. We talked about tossing a coin until the first time it comes up heads. In fact, in the same lecture where we saw this, is when we did that. It was about infinite probability spaces. And we learned that the expected value of x when p is a half, because we were only interested in fair coins, the expected value of x was 2 when p is a half. So in general, what's the expected value of x? Well, let's take a look at this thing. What do we know about x? So what's the probability that x is equal to some particular value I? So here we're going to use the fact that the coin tosses, each of the coin tosses are independent. And so that means that this is equal to the probability that, you know, the first coin toss is, I won't write it out, that the first coin toss is a tail, and the second coin toss is a tail, and the third coin toss is a tail, all the way up to the I-1th coin toss. All of those are tails, and then finally the ith coin toss is a head. And because those, because coin tosses are independent, that means that the probability that first one is a tail, the second one is a tail, and the third one is a tail, and the fourth one is a tail, all the way up to the I-1th one, and the ith one is a head, is just the product of those probabilities. So the first I-1 of them have to come up tails, and so that happens with probability 1 minus p to the I-1. That's the probability of one of them coming up tails is 1 minus p, and it has to happen I-1 times. And then finally, the probability that the ith one is a head, that happens with probability p. That's a really explicit description of the distribution. For every positive integer I, this tells you the probability that this random variable takes on the value I. Here's something else that actually makes computing the expected value easy. So the probability that x is bigger than or equal to I. What's that equal to? So when is x bigger than or equal to I? Well, x is bigger than or equal to I when I toss the coin the first I-1 times, and it always comes up tails. If that happens, then I will definitely have to toss the coin the ith time. So that means x is bigger than or equal to I. Right? So if I get I-1 tails for my first I-1 coin tosses, then I'm going to need I or more coin tosses before I'm done. So that means the probability that x is bigger than or equal to I is just 1 minus p to the I-1. And why was I interested in this probability that x is bigger than or equal to I? Well, I was interested in it because I want to know the expected value of x, and we just saw that sometimes that you can compute the expected value of x if you know this probability. And so let's use that. So the expected value of x, so let's check. Is x a non-negative random variable, integer valued? Yes, it's integer valued because it counts the number of coin tosses. And it's non-negative because you have to make actually at least one coin toss. So that's all good. So therefore, the expected value of x is equal to the sum, I equals 1 to infinity, the probability that x is bigger than or equal to I. That's equal to the sum, I equals 1 to infinity. We know what that probability is now, 1 minus p to the I-1. That's a little bit ugly, so we start counting with I equals 1 here. But whenever I shows up in this formula, it's actually I-1. So why don't we start counting from 0, and then we won't have to subtract this 1. So we start counting from 0 to infinity, and then we can replace I minus 1 with I. All right, so now we have a sum, I equals 0 to infinity, 1 minus p to the I. P is between 0 and 1, and let's be careful here. If you want this random variable to be interesting at all, meaning that the coin doesn't always come up tails and it doesn't always come up heads, then you should probably take p to be strictly between 0 and 1, because if p is 0, then the coin always comes up tails, and if p is 1, then the coin always comes up heads. That's kind of uninteresting, and you can, if you want, you can compute those expected values. But if the coin always comes up tails, you have to do an infinite number of coin tosses. If the coin always comes up heads, you only have to do one coin toss. So that's not so interesting. So if p is between 0 and 1, then what we have is this geometric series here, right? So 1 minus p is between 0 and 1, so that's our x. So this tells us that the sum of that geometric series is 1 over 1 minus p, right? That's 1 minus p is our value of x, and that is just equal to 1 over p. So write that down there. The expected value of x is 1 over p. And does that agree with what we've seen before? Yes. If I, okay, so pause. So someone asks, why don't we need to multiply by p for a probability that x is bigger than or equal to I? Well, that's what comes from here, right? So the definition of expected value that we've seen, the one that we, or one of the two that we've seen, says that the expected value of x is the sum over I of I times the probability that x equals I. So this is the usual version. And here we're showing that actually if you take the probability that x is bigger than or equal to I and sum that, well, you end up with the same thing, because the probability that x equals 1 appears once in the sum. The probability that x equals 2 appears twice in the sum. The probability that x equals 3 appears 3 times in the sum. So the difference is this is with x equal, this is the definition you use, where you use probability that x equals I, you multiply that by I, or you can use the probability that x is bigger than or equal to I, in which case you don't have to multiply by I. And so we use this one here, and the reason we use it is because, well, it leads us to this nice geometric series. So it leads us to this formula that we already have in our back pockets. No, 1 minus p, there's a double negative here, right? Negative, negative, that makes a positive. So you get 1 minus 1 plus p. Okay. All right, so the expected value is 1 over p. We've actually done the calculation earlier in the course with p equals 1/2, and indeed we saw that when you toss a coin that comes up heads with probability 1/2, then the expected number of coin tosses until you get the first head is 2, not surprisingly. And this tells us something that maybe shouldn't be a surprise. let's say that the coin comes up heads with probability 1/3. So 1 out of 3 times it comes up heads is a way to think about that. Well, you might expect that you would have to toss it, on average 3 times before heads shows up, which makes sense, right? Okay. Now, if you didn't know this, so if you didn't have this in your pocket, you could still compute the expected value of x using this formula, and I'll just quickly do that. So it's just the sum I equals 1 to infinity of I times the probability that x equals I, which is the sum I equals 1 to infinity of I times 1 minus p to the I minus 1 times p, which is equal to, we bring the p out front, and now if we look over on this side, we see that we have seen a thing like that. Here it is. Right, so that's what this looks like. Sum I equals 1 to infinity of 0, x to the 0. Yes, sorry, this should have had it doesn't matter, but this can start at 1 or 0, because if it starts with I equals 0, this is just multiplied by 0 anyway. So really we have a sum that looks like this, so we can use the formula that's on the board there. So we still have the leading p out front, and it's over 1 minus, and x is 1 minus p. And that's all squared. Like before, 1 minus p is just p. So we get p times 1 over p squared, and we get p. Okay. 1 over p. So the p on top cancels out one of the 2 p's on the bottom. So we get the same answer either way. That's a good thing. Hopefully that should be the case. Just somehow, in either case, we needed a little something extra that we hadn't seen yet. Either we needed to take the derivative of this thing that we have seen before to get this identity, or this alternate way of computing expected values of non-negative integer random variables. And if you think about it for a little while and you're sort of mathematically oriented, you'll realize maybe that's kind of doing the same thing but interpreting it a different way. Okay. All right. So let's let's leave that up for now. And we'll look at an application, and I'll start with a story that takes me back to my youth. I grew up in the country in a small town called Lac Ste. Marie, just about an hour and 15 minutes north of Ottawa. If you're a skier, you may have skied at the ski hill there, Mont Ste. Marie. And, you know, living in a small town, actually in a really rural area, not a lot of excitement, not a lot of sort of things going on. So, you know, the highlight of my week was when my father would go into town and buy groceries. Big exciting trip to the grocery store. Not because I cared particularly about groceries. Food was not really a high priority thing for me back then. But because I cared about breakfast cereal. And I didn't care about breakfast cereal because I felt like eating breakfast cereal. I cared about breakfast cereal because, and this shows you that I'm quite a bit older than you, because this is probably no longer legal by the time you were born. Back then, every box of breakfast cereal that was marketed towards kids would have some kind of collectible prize in it. So, you know, the breakfast cereal that you liked had maybe, there were 20 different toys that you could, that went along with that brand of cereal, and each box contained one of those toys in it. Okay? So every week we'd go into town, and I couldn't wait to get the box of cereal. You know, on a good week, if I was patient, as soon as we got home, I would tear the box of cereal open, dump the whole thing into a giant bowl, and grab the toy out. After that, I could care less about the cereal. You could have thrown it in the garbage for all I care. I just wanted that toy. And if I was really impatient that week, then I might sneak into the back of the truck and tear it open in the back of the truck before we even got home. Then there'd be a mess of cereal all over the bed of the truck. The advantage of doing it that way is I didn't even have to bother eating the cereal then. Okay, so all right. So the point then is, right, each time a box of cereal comes, there's a toy in it, and there's like 20 different toys, or n different toys possible. And so, you know, you think, oh great, each week you get a new toy. Well, that's not really true. You don't get a new toy necessarily each week, because it's possible that when you go there and you open the box of cereal, what you find is a toy that you already collected in some prior week. And so then that naturally raises the question, well, how many weeks does it take before I collect all n toys? Okay. So, you know, how many boxes of cereal do I have to open before I get all of the toys in the collection, all the 20 toys, or in general, all of the n toys? Now, in the literature, that thing is called the coupon collector's problem. Okay, so you have a set, I don't know, of n coupons, and let's just call them 1, 2, 3 up to n. Might as well be collecting integers. As far as the math is concerned, it might as well be integers that you're collecting, not toys. So you have a set of n coupons, and let's say C1, C2, C3, and so on. Let's say all the way up to infinity. You live forever and you keep buying a new box of cereal every week. Is an infinite sequence of coupons, and you know, and let's say these are independent, and the probability that that any particular coupon is equal to any particular value is just 1 over n for any I and any j. So this marker is becoming useless. As an aside, this whole experience has reminded me why I hate whiteboards. Markers fail. They're a terrible environmental disaster. There seems to be no form of refillable dry erase markers, so teach a few classes with one of these plastic markers and then throw it in the garbage. Not so good. And worst thing is they kind of fail unpredictably. Yeah, this is supposed to have some level marker thing on the side that tells me how much ink is left in it, but I can't see anything. It just looks pure black to me. And so yeah, they run out in the middle of class, then you have to go and hunt for a marker. So all that to say, I kind of wish I had installed chalkboards here because, well, when you use up a chalk, there's nothing left to throw in the garbage. And you can tell when you're getting close to the end of a piece of chalk, and you can even stretch chalk by like really pinching the last little bit in your fingers. I can't wait to get back to a place that has chalkboards. Anyway, all right, so all this to say, you have this infinite sequence of coupons. Each coupon is an integer from 1 to n, and you know, let's say I'm gonna say x is equal to, well, let's make it the minimum I such that C1 union C2 union C3 union CI is equal to 1 to n. That's a complicated sounding thing. That's just the number of weeks required to collect all n toys. This is what I'm interested in. How long does it take me? How many weeks do I have to wait before I get all of the toys in the collection? So that means that if I take the union, the set theoretic union of everything, then I get 1 to n, and it's the minimum. Right, the first time that happens, it's over. I'm definitely going to stop buying that brand of cereal at that point and move on to another brand. Okay. All right. And so I would like to know, what is the expected value of x? So that's called the coupon collector's problem. For the coupon collector's problem, these things are coupons, you know, the things you clip out of, well, they're Groupons, let's say. Coupons used to come in newspapers and you'd cut them out every week. There'd be something different. But actually the cereal box version is better, because really when you go to the store, if you want, you can pick a random box of cereal at the store, and really what comes out is, if they're packing the same numbers of toys in each, they manufacture the same number of different toys, then indeed what you get is basically something that's equally likely to be any given toy on any given week, independent of what happened the weeks before. At least something closely approximating that. All right. Okay. So how are we gonna compute this? Well, this looks hard, and it is. It's not trivial. So we'll use a strategy that often works, which is we'll just keep somehow defining things, letting the problem soak a bit by defining different aspects of it until hopefully the problem just falls apart. So this is something that is sort of well known in mathematics. There's two kinds of problem solvers, or if you like, there's two ways to crack a nut. So one way to crack a nut is to go and get a hammer and smash it. That happens quickly, but it requires strength and the right tool. Another way to crack a nut is to soak it in water for a long time, and then eventually you can just open it. It just kind of swells open. And we're going to try the soaking technique. So we'll just keep looking at the problem and tearing it apart until just somehow the answer becomes easy. Okay. So really here, another way to think about X is how many weeks do I have to wait before I have n different coupons or n different toys. So you can think of, that's another way of saying X. How many weeks does it take me to get n different toys? And if you think about it that way, well then you realize there's other things I could study, like how many weeks does it take me to get 2 different toys? Or how many weeks does it take me to get 5 different toys? So let's just define for each I in 1 to n, let xi equal the number of weeks required to get I different toys. So, you can imagine, here's the weeks, and, I'll put little dots here that indicate a new toy that I never got before. So actually the first week, you'll always find a new toy, right? The first time you go and open this new cereal you've never tried before, the toy you find in there is new. But then you may have to wait a little while before you get the next toy, and then you may have to wait even longer before you get the third toy, so that's different from the other ones, and so on. And eventually there's an nth one. And so what is xi then? Well, x1 is just this, right? So x1 is how many weeks did I have to wait till I got the first toy? Well, basically the first week is when it happened. x2, so this thing here is what we'll call x1, and this thing here is what we call x2. It's how many weeks I had to go to the store until I got the second toy. And then this one is x3, x4, and finally the last one, the one that I'm really interested in, is xn. How many weeks did it take me to get until I got the final toy? Okay. Good. And you can think, okay, well, this made some progress because I know the value of x1. Right, x1 is always 1. The first week I always get a new toy. So that's a good thing to know. But I don't know the value of x2 or x3 or x4 yet, and I certainly don't know the value of xn yet. So let's just leave aside what we saw, that the expected value of a geometric p random variable is 1 over p. All right. Okay, let's define something else then. Define yi is equal to xi minus xi minus 1. Okay. And this is for I is in 1 up to n. And for that, we'll just use a handy definition that x0, how many weeks do we have to wait before we have 0 toys? We don't have to wait at all. Before we even go to the store, we have 0 toys. So x0 is equal to 0. Then this makes sense even when I equals 1, because yeah, this is then x1 minus 0. All right. So what do these y's look like? Well, let's say y1 is x1 minus x0. So it's x1, there's x1, minus x0, so it's actually this thing here, right? It's 1 minus 0, so that's the value of y1. What's y2? Well, y2 is x2 minus x1. So if you think of it in terms of the length, that's what y2 looks like. It's actually the number of weeks we had to wait from the time we first got one coupon, one toy, until we got another toy, a new toy. And y3 is this thing here. And y4 is this thing here. Okay. And the picture shows it, but we can just check as well. If I sum I is equal to 1 to n of yi, well, then the definition says that's the sum I equals 1 to n of xi minus xi minus 1. And that, we can write it out longhand. The first thing in here is x1 minus x0. That's when I equals 1. The next thing in here is x2 minus x1. The next thing in here is x3 minus x2. And this goes on up until the end when we have xn minus xn minus 1. And if you look at this series, you see, okay, here's an x1, but there's also a matching minus x1. So those two things cancel out. Here's an x2, but if I look 1, 2, 3 more terms down, there's a matching minus x2. So those cancel out. And here's an x3, and if I looked a little bit further, in the next step I'd see x4 minus x3. That would cancel out. And in fact, everything cancels out except for plus xn and minus x0. But x0 by definition was 0. And xn, also by definition, is the value x that we're interested in. Okay? So this gives you this telescoping sum, which you can see in this picture. You can interpret it as, well, how many weeks do I have to wait before I get all n prizes? Well, it's the number of weeks before I get the first prize. And then the number of weeks after that first prize before I get the second prize. And the number of weeks after getting the second prize before I get the third prize. And so on. Of course, that will just give me the total number of weeks until I get the last prize. That's all this is saying here. Okay? Good. So, that tells us that the sum I equals 1 to n of yi is just x. It's the thing that we're trying to study. That means that the expected value of that sum is equal to the expected value of x. So, expected value of x is equal to expected value of that sum. And now we're going to use the thing that we almost always do when we have an expected value of a sum. We'll take the sum of the expected values. All right, so now we need to know this expected value of yi. Okay, so what is yi? So if we think about what yi means, this is, we already have I minus 1 toys, right? And now we're asking how long, so yi is how long we have to wait before getting a new toy. And by how long we have to wait, I mean how many boxes of cereal we have to buy until we find a new toy. Okay, so so I collected my I minus 1 toys, and now I go to the store the next week. What is the probability that I get a new toy? Well, two things can happen when I go to the store the next week. I could get one of the I minus 1 toys that I had before, or I could get one of the toys that I didn't have before. So, so for any particular week, you can imagine I go to the store, I blindly take a box of cereal, and with probability I minus 1 over n, I lose that week. Okay? I don't get the new toy. And with probability 1 minus I minus 1 over n, I get the new toy. But wait a minute. That sounds a lot like I went to the store that week and I tossed a biased coin. The coin comes up heads with probability, what did I say? It would be n minus, so there's I minus 1 toys that I don't want to get, but any of the rest of them I'm happy with, and what I get is a random one out of the n possible toys. And the probability of tails is I minus 1 over n. So yi here, how many weeks I have to do this before I get heads, before I get a new toy that I haven't seen before. And then that determines. So it's really another way to think of it. How many times do I have to toss this biased coin that comes up heads with this probability and tails with this probability until I get my first heads? That's the new toy. Well, the number of times that happens is a geometric random variable. And what's the probability in that geometric random variable? So let's clean this up a little bit. N minus I minus 1, that is n minus I plus 1. So that says that yi is a geometric p random variable for this value of p. Okay. And so the expected value of yi, the expected value of a geometric p random variable is 1 over p. So the expected value of yi is 1 over this. So we have to flip this thing. Good. So now we can continue here. All right, so we have a sum here. Looks confusing. Let's try and make it as simple as possible. So one thing I notice immediately about this sum is that there's a factor of n in every single term. So let's just pull that n out front. So the n can go here, and then we get a 1 over here. Now again, this thing on the bottom is confusing to me, so we can either manipulate this thing and hopefully we don't make a mistake, or we can just write out a few terms and see what it is and then see what happens there. So when I equals 1, what do we get? When I equals 1, we get n minus 1 plus 1. So that is just n. So that first term is 1 over n. Now what's the second term? When I equals 2, it's n minus 2 plus 1. So that second term is 1 over n minus 1. Well, now the third term, this gives me an n minus 3 plus 1, so it's 1 over n minus 3. And what happens when we get all the way to the end, when we have an n here? We get n minus n plus 1, so that's a 1. We get a 1 over 1. And if we just back off one step, let's say we put a I equals n minus 1 here, we'll get a 1 over 2. That's what this thing looks like. So actually, if we read this backwards, this is 1 plus a half, plus a third, plus a quarter, plus a fifth, and so on, all the way up to 1 over n. So this is just I equals 1 to n of 1 over n. And look at that. Amazingly, we know what that's called. It's the nth harmonic number. Great. So, so that's it. That's our answer. Expected value of x is the expected value of the sum of the yi's, and each yi is a geometric random variable for some value p, and those value p's end up being 1, 1/2, 1/3, 1/4, and so on. And so you get n times h of n. So, you know, so, and now, well, what does that look like roughly? Well, that's something, h of n is between log n and log of n plus 1, the natural logarithm of n. And so the number of weeks that you have to wait is the number of prizes times the natural logarithm of the number of prizes. Okay. So it's not a constant times the number of prizes. It's something that grows a little bit slowly. Okay. All right. Before nhn, is it 1 over n or 1 over something that's typeset as an L or before nhn? Oh, you're right. This should be 1 over I. 1 over 1 plus 1 over 2 plus 1 over 3 and so on. All right, so the answer is it takes exactly the expected number of weeks before I collect all the prizes is n times the nth harmonic number, which is almost the same thing as n times the natural logarithm of n. Okay. So, and I think this is one of these ones that is, this was really soaking, because we basically got there by breaking the problem down, understanding xn is really made up of a bunch of different things, really writing xn somehow as a sum, and there you get lucky that that the sum, those things that you're summing just happen to be random variables that you understand, geometric random variables. Why is it 1 over n minus 3? Yeah. 1 over n, 1 over n minus 1, 1 over n minus 2, and so on. So write this thing out longhand. This is when I equals 1, I equals 2, I equals 3, I equals 4. This is what you get. All right. Good. So that was the geometric distribution and an application of it. As you can maybe imagine, the geometric distribution shows up all the time because there's just tons of experiments where you're waiting for something to happen, right? Events keep happening and you're waiting for a particular event to happen. And, you know, that's sort of like tossing a biased coin and waiting for it to come up heads. How many times do you have to toss before it comes up heads? That's a geometric random variable. How many times do you have to run the experiment before the event you're interested in happens? That's a geometric random variable. So these geometric random variables, they show up all the time. I will mention one thing about them that just so in case you hear it, geometric random variables have what's called the memoryless property. And what the memoryless property means, and it's easy when you understand them, I mean, formally, it's this: the probability that x is bigger than or equal to t plus c, given that x is bigger than or equal to t, is just equal to the probability that x is bigger than or equal to c. So this is called the memoryless property for the following reason. So this is a conditional probability, and the condition here is I've been doing this experiment t minus 1 times, and the thing that I'm interested in hasn't happened yet. I tossed the coin t minus 1 times, and I have not seen a heads yet. So what's the probability that I have to toss the coin this many more times? Okay, this c times. Well, it's not surprising that that's the same thing as, you know, the probability that I just have to toss the, maybe this is given that x is bigger than or equal to t. Let's say t minus 1. Yeah. I toss the coin t minus 1 times. What's the probability that I have to toss it this many more times? So t plus c times. That's the same thing as if I hadn't done any of those previous coin tosses. And I'm just asking, all right, I started this from scratch. How much longer do I have to wait? So you may hear this term, the memoryless property. That's what this means. And it's handy sometimes in calculations, because it means it doesn't matter what the history of this experiment was. It's like I'm starting from scratch each time. And hopefully, intuitively, you guys recognize this, right? If I toss a coin 3 times in a row and it comes up tails, hopefully you don't think then that it's more likely to come up heads the next time you toss it. It's still just as likely to come up heads with, it's still going to come up heads with probability a half the 4th time you toss it. Okay. So the last thing is the binomial distribution. So the binomial, it actually has 2 parameters, np. So here's how you define it. Toss a biased coin, and biased coin, I mean the same definition, comes up heads with probability p, and tails with probability 1 minus p, n times, and b is equal to the number of heads. Okay. So why is this called the binomial distribution? So I toss the coin n times, and then I count the number of heads. That's this binomial random variable. And it's called the binomial NP random variable. Why is it called the binomial thing, random variable? Well, because the expected value of b, I can sum. I can sum over the number of heads, right? So how many heads could there be? There could be 0 heads, or there could be all the way up to n heads when I toss a coin n times. And all right. So how many ways are there to get, so if I imagine I write down my coin tosses as a sequence of heads and tails, and if I get exactly I heads, let's go to k as our summation variable just to make it more familiar looking. How many ways are there to get exactly k heads in a sequence of n heads and tails? Well, we've seen this many times, right? This is a string of h's and t's in which the number of h's is exactly k, and so the number of such strings is n choose k. We typically talked about them as binary strings, and we were looking at the number of binary strings with exactly k ones, but there's an n choose k there. And for each of those strings, what's the probability that we get that string, right? So we have tails, 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 heads, tails, tails, heads. So just look at one of those particular strings. And here's the example when k equals 3. Here's one of the strings that has exactly 3 heads in it. What's the probability of this particular sequence of coin tosses? Well, the tails came up with probability 1 minus p. This one also occurred with probability 1 minus p. This also with probability 1 minus p. But this one was a p. And then more 1 minus p's, more 1 minus p's, but then a p. And so on. And coin tosses are independent, so each of these, the probability of getting exactly this outcome and this outcome and this outcome and this outcome is just the product of these probabilities. And if we look here, well, we see that we have 1 minus p appears n minus k times, and p appears k times. So that gives you the formula for the expected value, and all that is just because by this argument here, the probability that b is equal to some particular value I is just, or k, is n choose k. It's the number of strings with k heads in them, and for each of those strings, the probability that you get that particular string. So this is the definition of the binomial distribution. It comes up when you toss a coin n times. So a biased p coin. So this tells you exactly the probability for every k that you get exactly k. If you compute its expected value, you get something like this, which looks difficult. So I wouldn't want to have to beat this up, but actually, maybe we can do better. Well, b is the number of heads. Is there another way to write b? Well, we can say for each I in 1 up to n, let bi equal 1 if the ith coin toss is heads, and 0 if it's tails. Then if I want to count the number of heads, that's b. That's just the sum, I equals 1 to n of bi. Right? Count to 1 if it's a heads and count 0 if it's not. And therefore the expected value of b is the expected value of that sum, which is, as usual, the sum of the expected values. But bi is just an indicator random variable. It has values only 1 and 0. And we've seen the expected value of such a random variable is just the probability that it's equal to 1. And the probability that it's equal to 1 is the probability that the coin came up heads for that particular coin toss, and that's just P. So this just becomes the sum I equals 1 to n of P, which is P times n. So this is just a basic application of what we saw last class of using indicator random variables. Gives us P times n. And that implies, well, this is also the correct formula for the expected value of B. So this crazy sum here is just P times n. So that's this, this counting two different ways somehow proves this weird identity, but just by looking at the expected value of B. Is memoryless related to independence in any way? Well, memoryless in this case comes out of independence in the sense that the reason that it's memoryless is that the coin tosses that define the geometric random variable are independent. So in particular, those first I minus 1 coin tosses, the condition that they are all equal to tails has no effect on the probabilities that any subsequent coin toss is equal to heads or tails. So it arises from independence for that particular thing for geometric random variables, but there are other memoryless random variables. In particular, in the continuous setting, there's the exponential random variable, which is a continuous version of the geometric random variable, where there's not really a notion of independence involved, because an exponential random variable isn't defined that way. It's just defined by its distribution, and it just so happens that its distribution has this memoryless property. Could I have used Newton's formula for binomial coefficients? Yes, I could have used Newton here, but there'd still be some work to do. There's one case where it's particularly easy, and actually if you followed through with that case you could get the whole thing. But when P is equal to a half, then 1 minus P is always equal to a half, right? So then this thing here would always be 1 over 2 to the n. And we have seen that the sum of the binomial coefficients running k equals 0 to n of n choose k, that's equal to 2 to the n because it's equal to the number of subsets of an n-element set, right? That's what that counts. So then this sum without any of the p's is 2 to the n, and if p is a half, then each one of those is divided by 2 to the the whole thing is divided by 2 to the n. So so that's the idea there. But it's not. Yes. So you get a thing that sums up to 2 to the n, and not even then. It takes a little bit of work. Much easier to use indicator random variables to do this. All right. So these binomial things, you will see them later in this course and in later courses. For now, see the unsurprising result that the expected value of one of these things is p times n. If I toss a coin that comes up heads with probability p, then I do it n times, it's not that much of a stretch to realize or expect that on average I will see p times n heads in my coin tosses. But there's a lot more interesting things about binomials that we'll see a little bit later in this course, and you'll see them again in subsequent courses. Okay, so that's it. We're out of time today. Anybody can ask me a question or two for the next minute or so. In this formula for the expected value, you need to multiply by k. That makes more sense. All right, so thanks again for showing up, and I will see you either this afternoon or on Monday.